Hello everyone, my name is Sahitha Karapitiya from Biological Systems Engineering, University of Wisconsin, Madison. My supervisor is Professor Chris Choi, and Dr. Hangul Chang and Dimut Pandiratna are co-authors in this research. Well, I'm going to present my research, our research on the CFD-based system design and optimization of a positive pressure precision ventilation design to mitigate heat stress in dairy cattle. Well, imagine for a moment if you go outside in a sweltering summer day with intense heat bearing upon you. What will you feel? You will feel so uncomfortable. What if you just became a dairy cow? Neither you can escape that relentless heat, no, you can tell your farmer in a more meaningful manner that I'm heat stressed. Well, therefore, as my colleague Dimut mentioned very clearly, heat stress is one of the most crucial problems that the dairy industry facing today, at least in Wisconsin. So, dairy barn's ventilation system is essential to any effort that we put on to prevent heat stress. Well, what are the systems that we have right now? As you all know, it's very clear that we have two systems, natural ventilation and mechanical ventilation. With the consolidation of large dairies, like small dairies into large dairies, and increase in the size of dairies, more managers prefer to go mechanical ventilation just because of their effectiveness. But still, it has its own inherent limitations as well. If you look at the mechanical ventilation, there are issues with airflow distribution and efficiency. You know that in current ventilation systems, there is limited control of the animal occupied zone, right? As my colleague mentioned, the air tends to move over the animal occupied zone, whereby not cooling each cup individually. Not only that, when air moves through this animal occupied zone, it picks up thermal energy, dust particles and moisture, degrading the air quality. Well, so what are we working on? What are we proposing? This is a new system. Let me call it AirJet system, but it has a fancy name, Positive Pressure Precision Ventilation System. This overcomes most of the limitations that we have in the prevailing mechanical ventilation. It's an innovative system that overcomes these limitations. It has a pressurized plenum and a series of AirJet nozzles. So this AirJet system has nozzle discharge to precisely tackle each cup, and these nozzle parameters vary. When the nozzle parameters vary, the airflow patterns vary. So therefore, we have come up with this study to investigate, to describe a design optimization system involving a series of CFD or computational fluid dynamics simulations that provided us with insights to establish ideal design parameters for the system's AirJet nozzles. Well, moving on, there is a sheer number of design parameters that you can look into. Just look at this example. We have used two nozzles and just 5 parameters. What are they? Like diameter, length, 2 positions and 1 angle. Just with these 5 parameters, it gives rise to 1440 different cases, 1000 plus cases. Just adding more parameters would increase the number of possible cases. So you can understand that the only solution that we have to evaluate is a computational method. So we went on for a computational method. So this is the computational domain that we have created with the boundary conditions shown over here. Well, you know that to rely on any computational fluid dynamic simulation, we need to validate this model against field data. So we came up with a sectional PPV or AirJet system to validate our model. Using the field data, we validate our model. Let's look at the validation. So validation of the computational simulations. So you can see that we have compared the velocity measurements that we took from the computer simulation directly with the corresponding coordinates of the physical model. And as shown, you can see that like the measurements that we have taken align broadly with the two models, the physical model that we created and the computational fluid dynamic model. So thereby validating the model that we created. Not only that, this shows us two different things about the PPV or the AirJet system. It shows that the uniformity is really good in the AirJet system, and as the distance from the nozzle increases, the area covered also broadens. So with the confidence of validating our AirJet system, we move on to the computational fluid dynamics experimental sequence. This is how we optimize the design parameters for the nozzles. Well, we divided the design optimization into 3 steps as the nozzle angle, nozzle location, and nozzle dimensions. So after the optimization, we look at 3 different case studies just to describe and demonstrate the advantages of this proposing ASABE system. Let's move on to the first comparison and evaluation of the design parameters. So if you look at here, we have compared the different nozzle angles. We selected 30 and 0 angle just because in a head-to-head stall, when you increase the angle, it creates an impinging zone. So we had to limit ourselves to 30 and 0. But at the end we found that there is minimal difference in the effect that the angle creates. So we selected the straight angle or the 0 degrees. And also we selected 10.2 centimeters, which is equal to 4 inches as the optimum nozzle diameter. So you also have a question, then where can we place this nozzle in the plenum? So we have a pool of candidates. From this pool of candidates, we narrowed down into 4 locations, and then finally we selected 2 locations. One at the neck of the cow and at the end, the tail end of the cow. And this is a nice comparison again, but a bit lengthy. Here we have compared the nozzle diameter and the length. As you can see, on one end you have the static pressure created at the nozzle and convective coolant. That's nozzle's number. So for those who don't know, nozzle number gives you an idea about the convective coolant, how much heat removed from a particular object. So it's really nice that if we go on increasing the heat transfer or the heat removal by decreasing the nozzle size. But in reality, a smaller nozzle will create a higher static pressure. So that would require higher grade fans and more power. So that's not feasible in reality. So we need to have a careful balance between these 2 parameters. Well, so that we have looked into the design parameters, now let's explore different case studies to show and demonstrate the advantages of this ASABE system. First, we have compared the conventional mechanical ventilation and the ASABE system that we are proposing. You can clearly show that the heat removed per cow is twice in the ASABE system. Dear colleagues, just look at this. This slide shows that the PPV or ASABE system significantly require less air intake, which is what we are looking for, the economic viability. So it requires 50% less air intake for the cooling performance with an enhanced cooling performance when compared to the conventional mechanical ventilation. So this is a staggering result. Well, and then air drift. So if you are from a dairy industry, you might be asking, well, what about natural wind? Yes, we compare the natural wind. You can see that when there is natural wind blowing, or we call it drift, there is a decrease in the heat removal. But you can see a nice result over here. When the speed of the drift reaches 1 meter per second, there's something happening. There's heat removal increase. At this point, we don't need mechanical ventilation. So we can reduce the speed of fans. And we are working on, our lab is working on a closed loop system where we can control the fans so that it depends on the microclimate or the microenvironment of the barn in order to automatically control the fan speed. We'll talk about that later. And then the final case study. Well, okay, we were talking about just 2 cow models. Then you'd ask me, like, what if? How can we really scale this up? Yes, we compare the scaling. We scale the barn into 16 cows to see if it is really feasible in the real world. So these are the results. So when we compare, you can see that the heat removal is uniform and there is no change in the velocity. Of course, there will be minor decreases. That's due to the discrepancies that we have in implementation, because other physical parameters, physiological parameters come into play, but it's minimal. Well, so far we have talked about evaluation, simulation, and things we do in the computer. But if you are from really dairy industry, you'd ask, then what are we doing in the real world? Here, we are building it to make it a reality. So this is my colleague Nirvana and Trey working on a module that we are going to put in a real barn. This summer and the next summer, we are really working on it to make it work in the real world. Well, and then this is how it look like in a real barn. So the blue color clipboard there is the ASABE plenum where the nozzles will be placed. Well, and also there's a good question. So we cannot build barns all of a sudden brand new, but we need to do some modification to the existing barn. Then is this really viable? How much modification are we going to do? look at this. There's minimum change to the existing barn. This is a real world barn. This is our experimental barn with hundreds of cows that we are working. We are only doing minimum changes to the existing barn walls, wall girds, and it would look like this. This is how once we do the modification. This is a cut in the wall girds and some modification that we are going to do. So we are also utilizing the existing resources in a barn to make it a reality. So here we have used the wood structures and the metal structures in the existing barn. This is how we place the plenum and how we take air from outside. And finally, so this would be the view of a barn when we implement our air system. This is a standardization and the modular design. So the barn we are proposing would look like this in the future. Are we going to stop here? No. We are moving towards an animal-centric ventilation system. We are going to build an intelligent closed-loop system where we can relieve the dairy industry of most of the challenges that they are facing. So our lab, with our collaborators, are moving towards this animal-centric closed-loop system. We are working on multiple projects in multiple fronts to achieve this in the near future. Well, okay, so to conclude, so this study proposed an ideal design parameter system for the fancy PPPV or the air jet nozzle system that we are proposing, and we have found out that the velocity of the air jets is more significant than the area it covered. Not only that, the proposed air jet system was found to produce twice the cooling performance and could reduce the air supply required by half compared to the conventional mechanical systems. And finally, the result shows that with the large plenum, enough to serve 16 cows, the pressurization is uniformly sufficient and that could deliver air jets at each nozzle exit at the required level. So I want to acknowledge our funding agency and our funding project. And thank you very much for being attentive, and I'm open to any questions. Thank you.
Thank you so much for the talk. It was wonderful. Your style of presentation was also great. I just had one quick question so you did simulation with 2 jets on 1 cow, and you did simulation with two jets on each cow for 16 cows.
Yeah, correct.
Why would you do that? What is the difference between both of those? Because why I'm saying this is because if you look at the whole PPV system, and have you tried modeling the whole PPV system? Because one of the key assumptions in your presentation is that the flow from the jet is constant. Yeah. I don't think it would be constant if the PPVs are in different locations where fans are only on the 2 ends. Am I incorrect? Or
yeah, so we have, if you look at the last slide over here, we have actually scaled it up. So the last case study, the third case study is this. So from our simulations, we were able to find out that the velocity is uniform. This is 16 cow.
So velocity is uniform in each jet across
Yes,
the whole
yes,
plenum,
correct.
if it's
Yeah.
straight airflow?
Yeah. But then there are discrepancies. Like this is lower, like minimum, like there's a minimum amount, like of difference. There is a difference, a minute difference than the 2 cow model that you can understand when you scale up, but it's still uniform.
Well, thank you. So this is now a break time.